Hello. I'm going to talk about data structures today. But somewhat unusually, it won't be about the persistent variety that we all know and love and use every day. Instead, I'd like to tell you a little bit about a data structure that goes by the name of ctree, which is mutable. It's meant to be modified in place. Now, clearly, for that reason, most people wouldn't want or need to reach for it by default. But nevertheless, I think ctrees are fascinating for what they are and for the way in which they bring some of the ideas behind Clojure-style persistent data structures and transients, and some ideas from the realm of concurrency research together to achieve a feature set uniquely their own. So firstly, by way of introduction, I'd like to mention just a few points on the evolutionary path that led to ctrees development. And undoubtedly, the correct starting point for that is Phil Bagwell's 2001 ideal hash trees paper, which introduced the data structure known as the hash array map tree in the literature, which we have come to know as in its persistent rendition as the persistent hash map in Clojure. Now, interestingly enough, that version of HAMTs described in that paper is actually mutable. Now, there are no fancy concurrency-related tricks in there, like those found in ctrees. But it's mutable nevertheless, and so that's interesting because that means in particular that it would have been in direct competition with hash tables in its design space. But even competing against hash tables as a possible basis for implementing an unsorted dictionary, HAMTs offer some compelling advantages, most notably a much more predictable performance profile. They just don't suffer the sort of, well, I need to resize myself, so you kind of need to hang around and wait while I do that, slow down. And in some scenarios, it's acceptable to trade some of the peak performance for consistent timings and basic operations, right? But of course, be that as may, when it was really with Rich Hickey's persistent implementation of this data structure using path copying to achieve persistence that it really came into its own, certainly from our point of view. So that happened in 2007. Additionally, Rich realized that the same basic idea could be simplified a little bit to implement a different abstract data type, and in this way, the vector was born, a persistent vector. And it is this 2007 persistent hash array map tree that is the direct evolutionary ancestor of ctrees as described in the first ctrees paper. However, what's really interesting is the version of ctrees described in the second paper. We'll get to those two papers in a second. And to understand those, it's good to have a look at transients first. Now, there may not be a direct causal link there because I don't think that paper mentions transients as an inspiration. So it's possible that that's an independent development. Nevertheless, in the order of idea, certainly in the order of study, it's good to look at transients first and understand exactly what they do and how they achieve those batch updates, speedups for persistent data structures, and only then to look at ctrees because they do a very similar thing, which just happens to be more complex. So vectors are, again, a Rich Hickey idea. Originally appeared in 2009, at first for the vector, and then later in 2009, Christophe implemented a transient-enabled version of the persistent hash map. And so it is the shoulders of these giants that would have been available to support further giants possibly interested in climbing onto them when the inventors of ctrees were starting to work on them. Fast forward 2 years, and the first ctries paper appeared. The second one appeared in 2012. There's also a reference implementation written in Scala with just a tiny sprinkling of Java. And so just to give you a quick overview of what ctries are, they're basically a map data structure which supports concurrent updates in a log-free fashion, which means global progress is guaranteed. Or in other words, if a group of threads manipulates a single ctree, then regardless of any scheduling infelicities, as long as the scheduler schedules some of those threads at least some of the time, then at least one of them is guaranteed eventually to make progress. And eventually means after a finite number of steps. Those operations that ctries support are pretty much the persistent hash map and transient hash map operations taken together. There's one exception, specifically the size operation is linear time, just because it's tricky to maintain a consistent count in a data structure that can be simultaneously changed from many concurrent threads. So I think it's a reasonable trade-off to just not have it. But I should certainly mention it because it is the one major performance degradation versus PHMs. Then on top of those basic persistent/transient hash map operations, ctries also support a constant time snapshot operation. And it's possible to make those snapshots persistent, but actually by default, they're just completely independent ctries, which share structure with the originals. Well, obviously, since snapshots are constant time. And finally, for this slide, I have ported the reference implementation to Clojure and added some niceties to hopefully make it somewhat nice to work with. And it's available for experimentation today. The current version number is 0.0.3. So that information will be repeated on the final slide. I hope you might feel somewhat inspired to maybe download it and type a couple expressions into the REPL, and then possibly forget it until such time as it might provide an opportunity to actually use it for something. Now, in implementing ctries.clj, well, the first order of business was to get the basic semantics right, but the immediate follow-on concern was to make ctries blend in somewhat seamlessly with the existing suite of data structures in Clojure. And for a split second, I may have entertained the idea of supporting the persistent and transient API simultaneously on the same object, right? But at second glance, that's clearly no-go because transients use some of the same Java method names with different semantics. So that can be done. Instead, ctries.clj maps are transient first. So if you create one, there's a factory function called concurrent map in the ctries.clj namespace. If you create one, what you get is a transient-like object with some extra guarantees. Namely those that if you assoc bang or disoc bang something onto or out of that map, what you'll get back is the very same map, and the original map will be modified in place. And so that means that you can write code in the usual functional style that you'd use with transients, but run it on multiple threads manipulating the same instance. And that's, I suppose, the encouraged way to use ctries in Clojure in most scenarios. What persistent does here, persistent bang, is slightly different to what it does with transients, because with transients, a call to persistent bang invalidates the transients, which can then no longer be used. On ctries, persistent bang is harmless to the original, and what it gives you as its as its return value is an immutable snapshot. And that immutable snapshot is a persistent map. It's slower than a regular persistent hash map, but otherwise it should behave more or less the same. And both those immutable snapshots and mutable ctries additionally support the deref operation, also spelled @, which creates mutable snapshots in the form of independent ctries. And so taking all of this together, what you can do is something like this. So what we do here is we create a ctree, then take a couple of snapshots, then bash the original ctree and the two snapshots in place in separate operations. Those could run on a single thread, on multiple threads, whatever. And then it turns out that all of those in-place modifications only apply to the ctree instances they were applied to. Right? So they're completely independent. And what we get is this version graph depicted in the top right corner of the slide, which is, of course, not unusual at all for a persistent data structure. But if you consider that those arrows and ellipses stand for arbitrary sequences of, well, sequences, collections of update operations potentially running on multiple threads in parallel with no user-level locking, then things become a little magical. And hence the choice of stars to represent ctrees. And really, this is the reason why I wanted to implement them. This combination of PDS-like version graphs and lock-free concurrent modifiability. I really wanted to know how that works under the hood. OK, but getting back to my original train of thought, this is the Clojure level API. But these are not all the features that ctrees have to offer. There's also a bunch of Java util concurrent map methods, which I have not so far chosen to expose as Clojure functions. And there's a number of reasons for that. The main reason, I suppose, is that I prefer to experiment with APIs for these outside of the main library. And at some point, I might fold in what seems to be the best approach into the library proper. I haven't done so far. But the features are accessible as Java methods. And as you can see, they all amount to swapping a key in or out of a map based on some condition related to the presence of that key, possibly with a particular value, in the map. And they're all atomic. So, say, put if absent could be useful if you wanted to instantiate a singleton object, but a singleton of the type that it's OK to construct multiple times in parallel, just as long everybody eventually only uses one version, and no other version is ever used, right? So you could have potentially many threads construct their own initial versions and then use put if absent to offer them to some sort of centralized cache. And then one thread will succeed in inserting a value, the other threads will fail, but put if absent will give them back the already present value in return, right? So they can then just switch over to that, to the singleton that won the race. And that sort of thing is used all over the place. Like last time I saw it in an open source project was probably in Hystrix with concurrent hash maps. Remove and replace are similar. Now, I wanted this library to be extensively tested, and I wouldn't say I'm quite there yet. In particular, I'm very much looking forward to those concurrency testing facilities of test checks to mature, and well, they're not immediately applicable to this data structure as it stands because they seem to rely on user-level scheduling and sort of controlled interleaving of operations. And some of the operations here, well, they just can't be pried apart easily. But I've been thinking about how best to pry them apart and to verify the semantics. with a test suite of that kind. So that's coming in the future, hopefully. But as of today, the test suite still manages to cover a lot of functionality, I think. So firstly, well, we have those immutable snapshots in there, which act as persistent maps, and it really is expected that they act as proper persistent hash maps. Well, if you're implementing a persistent hash map lookalike, then you should be using Zach Tellman's collection check. It's really a wonderful library, and so it has, in fact, it has given ctries.clj its stamp of approval for single-threaded use. So that's the first step in the overall strategy. Then we have those concurrent map methods. And for those, I use a similar approach, but it's custom built for ctries.clj test suite. I have a custom generator of operation sequences, and I compile those into Clojure functions and use them in test check properties. Ensuring that the C-tree resulting from the application of that function to an empty initial C-tree looks like, in several ways, like a concurrent hash map that the same operations are applied to. And then finally, there's some concurrent stress testing with long sequences of updates applied from several threads in parallel using the executive framework and some basic semantic checks at the end. So overall, it seems to work. I'd say that this is a somewhat robust test suite as it stands, and eventually hoping to add to it. Okay, and this, I would say, concludes the ctries.clj cheat sheet section of my talk. What I shall proceed to do now is scribble a ton of notes in the margins of this cheat sheet, describing various internal details which nobody is ever likely to need to know about when using these data structures. But it's really the whole point. I think that some of the concurrency-related ideas here may be more interesting than the data structure itself, at least at first, and then the data structure is wonderful for what it can do for you. But the enlightenment provided by some of the internals is amazing. So let's see if we have enough time to make that work. So to start. Well, as I said, the C-tree is a variation on the theme of hash array map trees. It's yet another family. It's yet another member of this family of data structures. And internally, it looks very similar. The most conspicuous difference is that where hash array map tree's internal tree might look something like the figure on the left. An equivalent C-tree would look more like the figure on the right, with the circles implementing nodes with volatile fields pointing to multi-way nodes like those found in regular persistent hash maps. The reason for this extra layer of indirection is that without it, if you wanted to not have it and yet still support concurrent updates from multiple threads, you have to accept losing some updates to race conditions. And the way in which that could happen is that, well, suppose that two threads wanted to update this data structure by associating two keys onto it. One of those keys would require the root node to be expanded. So it just happens to be a key that doesn't share those initial 5 bits of its hash value with the keys already present in the map. Okay, so that means that we'll have to replace the root. And then another key does share its initial 5 bits of 5 hashcode bits with the entries with the keys in the left-hand side child, in the left child of the root. So we also need to replace that child. In such a scenario, what could happen is that the two threads might race in such a way that the thread that wants to modify the root could succeed in doing that, but still use the old version of the left child node for the new root, even while the other thread descends the left path in the tree, looks at the left child, and eventually replaces it in the original root, right? But the original root is no more in the C tree. So in this way, we could lose the update to the child node here. With indirection nodes, this cannot happen because we never need to replace a child of a multi-way node. Any multi-way node only is guaranteed to have only inodes as children in direction nodes. And those might point to different children of their own at different times, but they do not themselves need to change during regular update operations. Okay, so in this way, races are prevented. And then this is the most conspicuous difference, but there's also there are also some other differences. So skipping forward one slide, and I'll go back to the previous one in a second. It's just a better split in terms of layout. The collection of nodes that ctries use internally doesn't look much like the collection of nodes that persistent hash maps in Clojure currently use. One reason for that is that I wanted to stay closer to the original paper for the initial implementation, just to make sure that if there are any problems, then there are problems with my implementation and not with the way in which I introduce some new feature. But additionally, performance evaluation of various node modifications is very much an open problem for me, certainly. It's a to-do item, and so I'm working on that on the side. Eventually some changes might land. As of today, we have those indirection nodes described a moment ago. Then they have so-called main nodes as children. And those, bitmap index node and hash collision node resemble the nodes of the same names found in persistent hash maps. Tomb node is a special node type used to ensure compactness of the tree in the presence of diss-soc operations. So C-trees actually shrink when you remove keys. That turns out to be somewhat tricky. Tomb nodes are a facility that makes this possible. I won't be going into that particular detail. And then there's also something called fail, which I will describe in some detail later on. And then finally, the actual key value pairs are currently reified in the form of singleton nodes in C-trees. That is not the case with persistent hash maps as found in Clojure today, and that's a significant optimization. So I suppose I'll have to see whether it can be fitted onto C-trees as well. Now, as I said, C-trees are in some important ways very similar to transients. They also track subtree ownership, but they track it in a different way, which we'll have a look at in a second. And additionally, they rewrite paths in different circumstances. So path rewriting in C-trees happens after snapshot operations. If you take no snapshots, then you never need to rewrite paths, even though you may keep modifying your C-trees. And when a rewrite happens, it's somewhat eager. So rewrites amount to replacing inodes, and this is actually a safe operation in this particular context. So normally you wouldn't replace inodes. Here it's okay because you're still replacing a main node with a main node with new inodes, basically. Well, anyway, this is performed eagerly. So the tree, so after snapshot, the tree, operates a little more slowly, but it fixes itself up very rapidly. And then what I think is most interesting inside the data structure is the pair of dcas for double cas or cas2-like operations that it uses to prevent modification to supposedly immutable snapshots of, to prevent modifications to ctries from affecting other ctries which they might share structure with. Right, and so, I think I swap them around somehow. So, okay. So, so going back to this point about ctries being similar to transients, well, this is how. With a regular Clojure-style transient, what you do when you perform an update is you proceed much like with a persistent data structure, except that at each step of your way down the tree, you examine a so-called edit marker, which is an atomic reference to something, to see if it happens to be the distinguished edit marker that the transient instance itself uses. If so, then you may presume that you own that particular fragment of the transient, that particular node, and you can just modify it in place instead of replacing it with a new node. And in this way, you avoid additional allocations. Basically, this is where the performance win comes from. But you need to make this check at every step of the way, and you do it just once. Now, in ctries, instead of an edit marker, you have something known as the generation marker. Inodes store generation markers, and the root node's generation marker is the distinguished one. And you still have to look at them at each level as you walk down the tree for post-snapshot fixer purposes. But when you finally want to make an update, what you do is you take the generation marker of the node which you wish to update and look back up to the root and compare it with the generation marker found there. So in transients, you have a relatively simple ownership check at each step of the way down the tree. In ctries, instead, the key ownership check that guarding your updates happens at the leaf node that you're modifying and involves the root. So somehow you need to make sure that nobody changed the node you're looking at in the meantime, while also making sure that root generation has not yet changed. So ideally, you do that using a cas2 operation, meaning compare and swap on two memory locations. Right? That just doesn't happen to exist in hardware, so we have to work around that using regular cas operations. But if we had access to a cas2-enabled hardware architecture, then that would obviously be ideal. And the reason why we have those generation markers in ctries in the first place is to support snapshots. Again, the mechanism for that is similar to something that happens in transients, where if you call persistent bang on a transient, that resets your edit marker to nil. It's an atomic reference to something, right? When you reset it to nil, that means it's no longer active and you are no longer permitted to make updates. In ctries, something similar happens when you take a snapshot. Snapshots discard old generation markers and install new ones, both in the original and in the new independent ctree. And the presence of a new generation marker in the root causes all accesses to internal nodes of the tree to update them to the latest generation first before doing anything else. And so it is in this way that path rewriting happens, and updates to things that shouldn't be updated are in this way also prevented. Okay, so for this to work, we need a cast2 operation. That's two-argument concurrent swap. And as I said, it's not a hardware primitive on most architectures today. But it turns out that it's actually possible to implement it in software using regular single-address concurrent swap operations. There are many schemes for doing that. And there's a number of desirable properties that one might hope to find in a cast2 software implementation. One that's very general and in many other ways particularly attractive was described in a paper by Harris, Fraze, and Pratt called A Practical Multi-Word Concurrent Swap Operation, which is based on single-address CAS operations and so-called descriptors. And ctries use RDCSS for snapshots. But then the problem with that, ctries use a sort of a precursor operation to cast2 described in this paper for snapshots. That's called RDCSS. We'll have a look at that in a second. But the problem with that is that, well, it uses those descriptor objects. And generally, it is to be expected of cast2 software implementations that provide data parallelism, which means that they can proceed concurrently as long as they access independent memory locations. They tend to be based on temporary descriptors swapped into those memory locations they operate on. And those descriptors generally need to be fresh. So it's not OK to reuse those objects. So it means that if we use this kind of cast2 implementation, then we just have to accept the cost of allocating those objects whenever we call cast2. Now, that's OK for snapshots, because generally speaking, you'd expect snapshots to be taken somewhat infrequently. But then regular updates really shouldn't be forced to pay this sort of price. It would never do to allocate an object each time you associate a new key into your map. Just wouldn't work very well. So for this reason, the second ctries paper introduces an original cast2-like operation called gcas for generational cas. And so I think that the feature set of ctries is one thing that's interesting about them. The other key thing that's interesting about them is how they use these two operations, and these two operations themselves are well worthwhile taking a closer look at. So this is what I'd like to do in the final section of the talk. As I said, there are two, and RDCSS is the more immediately understandable, the more basic one. The name stands for restricted double compare single swap. And it's restricted, well, in two ways. So the first way is that that the arguments need to come in a certain distinguished order. But I suppose the main way is that it requires memory to be partitioned into a control section and a data section. So you're permitted to make two compares and a single swap with RDCSS but you need to make sure that independent RDCSS calls happening in parallel don't treat, well, always treat the same addresses as the swappable addresses. Okay, so you need to know which addresses are your extra control compare addresses and which are the swaps. In ctries, this requirement is very simple to satisfy. Indeed, it's possible to restrict the operation a little even further because what we need for snapshots, for taking snapshots, is the ability to take the root indirection node and replace it with a new one pointing to the same main node. Right? We call that indirection nodes store generation markers. Those generation markers are fixed, and they're freshly allocated each time an indirection node is allocated. So if you manage to replace the root indirection node while keeping the old main node, that means we have a C-tree. We now have a C-tree which looks the same, but it's moved on to a new generation. So therefore, and then if we do it twice in parallel, if we take the same main node and install it in a new inode, then we now have two C-trees with the same main node. So that's how snapshots work. But again, we don't have a hardware operation to do that with. So the way in which RDCSS achieves CAS2-like semantics in this sort of scenario is it actually introduces a collection of 3 operations. 2 of them are expected to be used from user code. One of them is more of an implementation detail. RDCSS is the CAS-like operation which takes 2 compare addresses and 1 value to swap in. RDCSS complete is the implementation detail, and then RDCSS read is the operation that all read accesses to the memory locations involved need to go through. And the reason you can't access it directly is that nobody may ever see the intermediate objects that RDCSS places in some memory locations. What RDCSS does first, when it's asked to perform the 2 compares and possibly the 1 swap, is it creates a descriptor, which looks like this in Clojure. It points to the, well, in the case of ctries, it points to the old indirection node, the one you're hoping to replace, and the new one that you want to swap in. And additionally, it points to the old main node. So the main node here acts as the control datum. And the indirection node is the data part of the operation. So this gets swapped in place of the root inode. And then an attempt is made to perform some further CAS operations, and eventually, if those succeed, they may not necessarily succeed, but if those succeed, then the descriptor is replaced with the new inode, the proposed inode again. If they fail, then it is replaced with the old inode. The reason for the use of a descriptor is that of a descriptor object which holds all the information describing the in-progress operation, is that if the thread that initiated RDCSS stops, say, well, the scheduler forgets about it, and no longer gets to perform its work, then we need to make sure that other threads can fix this situation somehow, because, well, the data structure is supposed to be lock-free, so global progress needs to be guaranteed under any circumstances. And so what happens is that other threads, if they happen to notice that an RDCSS descriptor is present where they expect the root inode to live, they look at the descriptor and attempt to help in completing the operation. And this is a pattern you find all the time in this type of concurrency-related operation. In log-free data structures and weight-free data structures, threads racing to access a memory location frequently help each other to complete it before moving on to their own business. So this is what RDCSS read is for. It accesses the memory location, looks at the descriptor. If it finds the descriptor, it looks at the descriptor, it completes the operation or attempts to complete the operation, and only then does it read a value out of the memory location and hand it back to the caller. So this works great for snapshots, but again, it's not appropriate for updates, and therefore a separate operation is introduced for those. It's called gcas for generational cas. It also provides double compare single swap, and it's also restricted in that the two compares always on the same memory locations, and the swap is also always on the same memory location. Specifically, it compares the current inode's generation marker to the root generation marker, and then it attempts a compare and swap on the current inode's main node. Now, the design goal here is to do this thing, which is similar to what RDCSS accomplishes, but also not to allocate an intermediate descriptor if possible. So the alternative strategy that gcas uses is to use main nodes themselves as descriptors. And well, this is the one particular main node type that is only ever used as a descriptor mark, and it's only ever created if operations fail, and when they fail. And so you see, it has a get prev operation for getting the previous value. Basically, the idea is that a descriptor stores the original values and the proposed value for the new memory location. So with gcas, we don't create a descriptor. Instead, we just swap in the proposed value optimistically, but it itself then serves as the descriptor for the operation because it has a pointer to the previous value of that field, which is only changed once. It's reset to nil when the operation successfully completes. And if it doesn't complete, then the old value is swapped back in, and we're done. And again, it's actually a collection of 3 operations because any reads of main nodes need to make sure that those are actually committed main nodes with nil prev pointers. If they're not, then they help complete them. And I was going to show you what one of these operations looks like in Clojure. I guess gcas is the original contribution of this paper, so might as well use it here. So this is it. When you attempt gcas, you take a proposed value of a proposed new main node. At this point, you are guaranteed to be the only thread in possession of a pointer to this node. So you set its volatile previous field. It needs to be volatile to preserve correct semantics to the old value. And then you attempt an optimistic cas. Well, if you fail, then you failed. But if you succeed, you then proceed to commit. So that's what you do as a client of the cas operation. As a client of the read operation, you call gcas read on an inode. It looks at the main node of the inode, and again, it does. Well, here we don't need to check if we need to commit. We guaranteed to have to commit. In the read operation, we check whether we need to commit, perhaps. And if so, we do. And the commit amounts to a loop which has a few places where it might terminate early, and it takes these exit points when a parallel operation does something in the middle that sort of invalidates this in-progress operation. But otherwise, it reads the root generation marker. Well, actually, the root I know then looks at the generation marker here, and performs a simple pointer identity check against the expected one. If that succeeds, then it commits the value. If that doesn't succeed, then it tries again, possibly decides if the generation marker actually changed, then it decides that the operation needs to fail. So it registers that fact immediately, and then goes back to the top of the loop, and this is where cleanup happens. And so clearly these cast2 operations, RDCSS is very similar actually. These cast2 operations have an internal structure that it is possible to examine, and in fact, if you wanted to, you could observe the intermediate steps in user-level code. But if you commit to this contract of only accessing those memory locations using gcas read and gcas, then you are guaranteed never to see those intermediate values. And in that way, the overall cast2 operation can be said to be atomic. You can't observe non-atomicity. OK, so these are the two operations that I think are fascinating here. There's any number of ways in which I think they could be used in Clojure. So hopefully I'll be able to make some additional library releases based on those. But if I won't, then maybe somebody else will. The library itself may hopefully also be useful to you occasionally. And I think with that, I'll call it wrap. Thank you.